Est-ce qu'on peut commencer?
Yes.
Bonjour, je suis très content d'être ici. Je vais vous remercier pour cette invitation, particulièrement au professeur Daniel Kaufmann. Maintenant en anglais. So, good morning, everybody. Thank you very much for this kind invitation.
You have to.
Right. Should I start again? Yes, good morning. I'd like to thank you very much for this kind invitation, and particularly Professor Daniel Kaufmann, with whom we had collaborated some years ago in Networks of Excellence, EuroNGI and EuroFGI. So it's a great pleasure for me to be here and an honor as well. So I'm John Stamoulis from Athens University of Economics and Business, and head of the Services, Technologies, and Economics group of our university. And today I'm going to give a talk on incentives in smart energy grids, particularly the approach we are developing in our project Resonance. So this is a brief outline of my talk. I will give an introduction about our research and about incentives in general. Then I will overview briefly our project Resonance, and then I will present the recent model we are working on optimal shared incentives for provision of flexibility in smart grids. So in these figures, we see, let's say, how the traditional energy grids have evolved to the new smart energy grids, in which we have bidirectional flow of information, but also bidirectional flow of energy, in the sense that we have not just the big generators on the one end and the consumers on the other, but we also have production at our homes, and that's why we use this term prosumers. So another, let's say, big difference is the use of renewables, which is becoming more and more extensive. And to this end, we have more variability and volatility in our productions, at the benefit, of course, of the environment, which is very important criterion. So if we consider, let's say, an ecosystem such as that of the smart grid, or also the digital ecosystem of the internet, even more generally, players are self-interested and have different roles and functionalities. And although they act complementarily in the value chain in order to for an end-to-end service to be provided to us, the users, they may have conflicting interests. For example, in the internet, we have the over-the-top providers like Netflix, for example, which produce lots of traffic. And we also have the network providers, which would like to control the congestion in their network. In smart energy grids, but both of them are very important for the provision of an end-to-end service. By the same token, in the smart energy grid, we have the producers and the network operators who have to coexist and collaborate together in order for the production to be delivered to the consumers. But also, the network operators care about the stability of their networks, while the producers, of course, in general, they are interested in selling the power that they generate. So in conventional optimization problems, let's say a few decades ago, we used to have resource allocation problems aiming to achieve a global optimum with a single criterion, possibly combining multiple metrics. And also this optimization would be performed by a centralized entity, often possessing full information. This such a modeling is not appropriate anymore for the situations where we have complementary functionalities by independent entities, but possibly conflicting interests, which situations we refer to as tussles. So the right objective for optimization in such situations is to look for an equilibrium. And also, we need distributed solutions aiming for equilibrium operating points and taking into account the interests of individual players, which of course we will see that can be affected by incentives, the large scales of the system, of the ecosystem, and the technology already in place, the distribution of information and the functionality among these self-interested players. So let me give you a brief example of incentive mechanisms, which, as I said before, can be a means of affecting, of shaping the interests of certain players, possibly at the benefit of all players. So we see here a very simple mechanism. I'm not sure if it's the case in France, but in Greece, in the supermarkets, we have this mechanism whereby we have to place a coin in order to make use of a supermarket, of a shopping cart. And at the end, we have to decide whether we are, very much in a hurry in order to leave the cart next to our car, but not collect back the coin, or fetch it back at the place where all the cards are and get the coin back. So this is, I think, a very clever incentive mechanism, because most probably if these were not in place, we wouldn't bother carrying the card back to the place where it is has to be collected. So in year 2007, the Nobel Prize in Economic Sciences was offered to Myerson, Maskin, and Hurwitz for the subject of mechanism design and their seminal research in this area. And so I have quoted here two brief statements by them. Myerson mentioned that incentive constraints should be considered co-equally with resource constraints in the formulation of an economic problem. And also Maskin mentioned that the mechanism design is the engineering side of economic theory. So they can help us attain an efficient outcome in a distributed way for complicated optimization problems. So, motivated by this, what do we do in our group in Athens University of Economics and Business? The group is titled Services, Technologies, and Economics. So we investigate, develop, and evaluate concepts and mechanisms in which we combine ICT knowledge, of course, because we are informatics scientists and engineers, and we make use also of business and economic concepts. So we see here that we have, let's say, unquote, the intersection of three different planes. Of course, the ICT technology. So we do this for smart grids, you see, for 5G and 6G telecommunications, for blockchains, for internet and cloud computing, Internet of Things, etc. So this is our context. But, sorry, we make use of economic models and mechanisms, like, for example, incentives, auctions, pricing, trust, and reputation. But we take also into account the formation of value chains. So to whom we apply these incentives, who, let's say, exchanges money and information with whom. This is the form of the value chain, and the business players involved in this, etc., in what we call business models. So we combine technology, of course, because this sets the scene in which we do this kind of analysis, with economic modeling and business modeling. And of course, I would very much be interested after the end of the talk if you see that we can collaborate in some way with this spirit of research. So this approximately completes the first part of my talk. So if you would like to have any questions up to now. So otherwise, we go to the second part. So among, let's say, the new capabilities that a smart energy grid has offered to us is the use of demand side management and or demand response. So both terms are used. So what's the idea? The idea is that we may have some, for example, in certain cases, some critical peaks, like for example in Greece, where the weather is very warm in the summer, in which cases we may have, let's say, very high prediction for a very high consumption. So what can we do in this case? We can either offer more produced energy in a smart grid from the production plants, or we can ask the consumers if they could possibly reduce their consumption and their demand, particularly during certain time zones, such as this one depicted in the simple figure, and by warning them, for example, that no, it's going to be very hot between 12 and 4 in the afternoon. So please try not to have the set point temperature of your air condition too low in order to avoid, let's say, a blackout. So we can have either a reduction of demand or possibly a shift of demand. Can have both of them, because if I just increase, sorry, the set point of my air condition, and thus I reduce the consumption, this is load, but just shaded load. It will not be consumed later. But if I just avoid, let's say, to operate my washing machine and I do it later in the night, then this is shifted load. But again, also shifted load is very helpful because we will avoid the peak and possibly have a higher consumption later, which hopefully should not be, let's say, another peak, because then what happens is a so-called rebound effect. So what are the benefits from demand side management? So reliability and reduced outages, also avoidance of putting in the grid in the so-called pool costly power generation units. Also several environmental benefits, because sometimes these let's say the more costly generation units are not environmentally friendly. They are operated by forces, etc. And also, we have an improved and more balanced system operation, particularly in the transmission and distribution networks. So, one way to do this is to just have, let's say, some central authority announce that please, we're going to have tomorrow, let's say, in the afternoon, a high temperature. Please try to reduce your consumption, particularly during those times. Another way is to introduce a new business role in the smart energy grid, which is the role of the aggregator. The aggregator, the DR aggregator, demand response aggregator, or flexibility aggregator, can coordinate users to reduce their demand and sell this reduction to the so-called flexibility market. So in this flexibility may be necessary either in a situation such as that I mentioned before, or let's say because the generation by renewable units was lower than that expected. For example, due to less wind than that predicted, sorry, or due to less sunlight during daytime. So in this case, in order to balance demand and supply, in cases where supply is lower, the aggregator can coordinate users to produce, sorry, to promise, unquote, that they will have less demand, and also, of course, to keep their promise. And at the same time, so this aggregator will be rewarded from the flexibility market because he will sell this reduction. But at the same time, in order to attain this, the aggregator should provide users with the proper incentives. Why? Because users, by consuming less than what they had in mind, they will suffer a discomfort, that is, a loss of utility. So the new consumption schedule, the reduced one, will not be optimal for the users anymore. And in order, let's say, to become equally good as the one they had, the reduced schedule to become equally good as the one initially planned by the user, the aggregator has to give them some incentives. For the time, we will assume that these incentives are economic ones, that is, a discount in their bill, or some direct monetary reward, or because often, let's say, if we compute these rewards on the basis of the discomfort, let's say the economic amount is very low, let's say it can be just a few euros, let's say per week, which is, we don't bother about such a small reduction. But we have seen in past projects that the users may care to, let's say, be rewarded by means of a lottery ticket and have a prospect of winning a much higher price with a low probability, of course. So I'm going, this is, let's say, flexibility market is, let's say, the context and for our project resonance. The complete titles are applicable and efficient solutions for optimal management of cross-sector energy. Sorry. And I will give you a short overview of our project, which is based on a presentation by our project coordinator, Markus Tauberger from VTT in Oulu, Finland. So, what are the main objectives of our project? Is to make it more cost efficient to harness flexibility from distributed and small scale assets in homes, buildings, etc., at a large scale. So we see here that we are trying to mobilize, let's say, apartment owners, let's say, everyday users, each of whom will have a small contribution to flexibility. But the objective is that we aggregate these small contributions and have a larger scale total amount of flexibility. So at the same time, the objective of the project is to assist this kind of large-scale flexibility offering by means of software. So to develop innovative software framework and facilitate the design and development of solutions that are standard compliant for demand-side flexibility management. So I will explain this in a minute. So the idea is for the project, and this is already in good progress, to develop a data and service marketplace in which we can upload software solutions for aggregation flexibility, and in which these solutions may be offered as services to interested aggregators or to interested retailers, etc. So, and of course, so we will, in this marketplace, technology and service providers will be able to advertise and their services, tools, and data assets. For example, data about energy consumption in conjunction with weather conditions data. And also others will be able to explore these services, possibly at a fee. So this is, so the project has, let's say, two, let's say, vertical and complementary dimensions. One is how to do this flexibility management in a better way, in a more efficient way, at a large scale on the basis of incentives. At the same time, the software that will make this happen to be, let's say, reusable by others. So to this end, the project is already developing catalog of software services for resource management, for customer management, and of course for aggregation, flexibility, and for market integration. I will show you first the map, unquote, of our project. So we have 6 pilot countries, and of course, you see there are several partners from industry and academia. And so we see that in each country, there's going to be a pilot, and we have a pilot cluster, as we call it, from each country. And so overall, we have 7 countries of partners, namely France, Greece, Germany, Denmark, Sweden, and Finland. And as I said before, the project is coordinated by VTT Technical Center, Research Center of Finland. So one of the main objectives of the project is to develop and test the original software catalogs for each of the 6 pilots. But the second very important objective is that the services that will be developed for each pilot, that they are replicated to another pilot site as well. So again, to demonstrate that this idea of data and service marketplace, where we can have reusable software by other players, is indeed possible. So the pilots combine diverse energy resources, like, for example, district heating, heat pumps, HVACs, photovoltaic system, batteries, electrical vehicles and their charging. So because in the very title of the project, we have the term cross sector energy management. Okay. And also we have different business sectors in each pilot. For example, industrial, commercial, residential, transportation. For example, in the pilot site of Greece, we combine, let's say, the conservatory of a city of Ptolemaida in Greece with the natatorium and the consumption, I mean, in these 2 buildings, and with some small apartments as well. So we see we have public buildings and private institutional private public buildings and private buildings at the same time. So this figure, which is very detailed, of course, just depicts these ideas that were mentioned before about the service catalogs, the aggregation platform, and who can use it, namely residents, building owners in office buildings, public institutions, etc. So we want to have demand response and flexibility management stemming from small energy assets at a large scale, which means massive aggregation, cross energy. So if, for example, district heating is less expensive at some point than energy, then we can switch some devices, some heating or cooling devices to district heating. And also make reuse of the software to be employed for this flexibility management in other pilot sites, and hopefully in the future, in general, by players in the market. So this completes the second part of my talk. And I think now it's time for some modeling and mathematics, which I hope you will also enjoy. So this is joint work with Professor Thanasis Papaioannou from National Kapodistran University of Athens, who is also a research associate of our group. So this work will be submitted soon in Smart Grid conference. So we will deal with a model for incentives for large-scale flexibility management. In the previous publications by Professor Papayuan and myself, an optimization framework for energy efficient management for prosumers, which was based on the work we had done in the previous ICT Smart Energy Grid project, again coordinated by VTT. The name of that project was iFlex. We developed a simple yet powerful and analyzed a simple yet powerful mechanism which proves to be particularly applicable for large scale. So the idea was that we have flexibility aggregators, and in order to incentivize the various consumers to provide some flexibility, he just announces one parameter, namely the amount R of incentives per unit of flexibility offered by each user. So he announces publicly this parameter, and then each user decides on the overall flexibility xn to offer, knowing that if he does offer such an amount of flexibility xn, he will receive a reward R times xn. So the user solves the so-called user's net benefit maximization problem, and he knows his own utility function, and he can decide on the flexibility to offer. And this actually can be measured by means of a smart meter at the user premises. So how does the aggregator select the optimal value of this incentive parameter R? So we have two cases. One is, let's say, the ideal full information case, in which the aggregator also knows the user utility function, and he can thus, let's say, predict what the user will do and estimate the user's utility, and then based on this, you can find the optimal R, or this would amount to stacking the game. So because I announce R, I know that the user will act optimally for his own interest. Of course, I can estimate the best response of the user in terms of the flexibility to be offered as a function of R, and then I can, for each user, and then I can decide on the optimal R for myself if I am the aggregator. So, but this cycle game requires full information of user actions, but the aggregator may not know user utility. So we have also developed a distributed and iterative solution for the realistic case where user utility functions are not known to the aggregator. And this is a simple mechanism, actually, and is suitable for large-scale systems, such as the one modeled by our project and studied by our project Resonance. So, in the sequel, I will now present a special case of this model, which we are still currently investigating. So the idea is that we have, let's say, an apartment building, like a community housing or a university dormitory, where we have a shared bill, so that we don't have a smart meter in each small apartment or in each room in the university dormitory. And we have a set N of consumers that share equally the total electricity bill in this apartment. So we have consumers 1 up to N. We would use the term consumers and users interchangeably. So the individual consumption is not measured. And to this end, also, the individual flexibility offered cannot be measured. So the aggregator aims to incite users to provide a specific amount of flexibility, X under bar, in the flexibility market. And if he's successful, he will earn V times X. So the aggregator promises to the flexibility market, let's say, this amount, and he will earn this much if he's really successful. So if this demand demand response event is successful, then when is this demand response event successful? If the total flexibility offered is at least X under bar. But even in this case, the aggregator will only sell with X under bar because this is the contract that he has agreed with in the flexibility market. So the total is so what incentives will be offered to the users? It's going to be R times X under bar, and these incentives may only be shared equally among the end users because the actions of each user are not observable to others, and of course they're not observable by the aggregator either. Okay? So the user M has to decide whether to participate in this DR event or not. So if he decides yes, he will produce a flexibility X sub n, which, as we said, is not observable. He will suffer a discomfort due to loss of utility because he will not consume his energy in accordance with the optimal schedule. And so this is the cost, unquote, of the user, and it's delta utility UN. So, but what will the user earn? He will earn a reward, which is his fair share from the total amount of rewards R times X bar, only if this DR event is successful. So in some sense, if deciding to participate in the DR event, the user will suffer a cost, this is sure, and he risks also to earn a reward in case of success. So the user will suffer the cost, but he's not sure whether he will earn this reward. So if the user decides negatively, that is, do not try to reduce his schedule, his consumption schedule, he will maintain his consumption and, of course, his utility. And if the DR event is successful, he will still earn the reward because it's not observable, but he has not exerted the effort to help the others to make this flexibility amount. So in this sense, such a user is free riding, as in the case of public goods. Sorry for a minute. So is, let's say, this user's dilemma clear? All right, thank you. Yeah, please, go ahead.
So it's not related to this specifically, but I had this question before. Who provides the money? It's the government. You're assuming that the government.
No, it's in the flexibility market. So
yeah,
yes, it's let's say we have several kinds of markets in the grid. For example, in Greece, there's a particular, let's say, government institution that runs, let's say, next day wholesale market, that runs market for the next hour, balance market, etc. So it's, let's say, these markets are kind of auctions. So if I can bid in this market if I am an aggregator and promise that I can offer this amount of flexibility, and then the auction is run and the amount of and the reward is cleared for the aggregator. Okay.
So the government should have some budget for this.
Or yes, but also it is important that this flexibility is attained because, for example, we may have lower renewable production than that expected or predicted. Let's say we may make our predictions for the next day for 24-hourly slots, but then the weather conditions may be different than what was predicted. Okay, and actually, this organization matches all these and demand and supply, etc. Okay, so it's not exactly the government, this institution, but runs the energy markets. In Greece, it's, if I translate, it's, let's say, energy market operator. Okay, but we don't have flexibility market here in Greece. So, in order to make our analysis a bit simpler, we assume a symmetric case, like for example, in a university dormitory where all the rooms or apartments are the same. And we assume that if a user decides to participate and contribute to the flexibility formation, she will offer not flexibility amount of his own, but a particular amount of flexibility. So all participating users offer the same amount of flexibility. For example, they turn off their washing machine, or they increase the air conditioning set point in summer by 2 degrees. They might actually, the aggregator may help the users by saying, please provide this flexibility, and how, give some hints, some suggestions on how to make this happen. So we assume that all participating users will give the same amount of flexibility, and they will suffer the same discomfort. Why? Because to make this model tractable. In case, when do we have a successful demand response event, where at least as many users as this N minimum decide to participate. And what is this N minimum? It has to be the ceiling of the total amount of flexibility X under bar sought over the amount of flexibility offered per user. A necessary condition for any user to participate is that it is possible that he will benefit. So if a user participating suffers a cost unquote, a discomfort which is delta U, then the likely but not sure reward, which is R times X over N, should exceed this discomfort cost. Because if it's lower, then the user never has any incentive to participate. So this is a necessary condition for a possibility to have a successful DR event. So, but since we have a user dilemma, we will look for an equilibrium. And in particularly, we denote by P sub n the probability that the user does participate in the demand response event. So the user dilemma is either to participate through the DR event, contribute to flexibility, and possibly be rewarded, because if not enough users participate, then he will suffer the cost, but he will not be rewarded. Or not to participate, that is to abstain, incur no discomfort cost, and be rewarded, but with a lower probability. Why? Because if, let's say, we need 10 users to make the target of amount of total flexibility, and I decide not to participate, then it's like demanding that from the rest 100 users, 10 participate. While if I participate, what I require is that at least 9 from the other users participate. So if I participate, it's more likely that the total amount of flexibility will indeed be aggregated. But if I participate, I will also incur the cost of discomfort. So in Nash equilibrium, in mixed strategy Nash equilibrium, we will have the condition is that the payoffs of these two actions are equal, so that the user is indifferent between participating and not participating. So the user, so what's the equilibrium condition? That the expected payoff of the user under these two actions are equal. So that is, if I decide to participate, my payoff is, sorry. If I decide to participate, my payoff is this much times the probability that the VDI response is successful, condition on the fact that I participate, minus the cost. If I don't participate, my payoff is this much times the probability that the DR event is successful, given that I don't participate, which is a lower probability than before, minus zero cost. So if we make these two equal, and after some algebra, we obtain a very simple form, namely that the probability that n min minus 1 other users participate is equal to this fraction of the cost over the individual user reward. And again, we see that, remember, we had a necessary condition that this is smaller than this amount in order for the problem to be meaningful. And actually, this is apparent again, why we start with this necessary condition, because if this fraction is greater than 1, it can never be equal to some probability amount, like some probability expression. Okay? So the intuitively clear necessary condition is also consistent with this equation here. And since we have assumed to make our lives easier that the equilibrium participation that the users are symmetric, also in equilibrium, the participation probability of each user would be symmetric. It would be the same for all of them, which means that this probability expression there is a binomial. So we have a closed form for this probability expression involving only this unknown equilibrium participation probability, and we can compute this numerically. And of course, this the solution of this equation depends on R, namely on the reward parameter promised by and announced publicly by the aggregator, but does not depend on the rewards actually earned by the aggregator in the market. So this is, let's say, interesting, and we will see the consequence of this. So we don't see this parameter V anywhere, okay? But of course, we have to make sure that once R is allowed, R of course should be lower than V, but we have to see what kind of profits the aggregator will also make at the end. So if the DR event is successful, the aggregator's net profit will be the amount earned from the flexibility market, which is V times X under bar, minus the rewards offered to the users. So the expected payoff of the aggregator is the difference of these two quantities times the probability that the DR event is successful, which is the probability that at least n min users participate in the DR event, which again is the expression of the binomial upper tail with success probability P equilibrium. So now the aggregator can compute knowing for each R what the P equilibrium is. He doesn't know it in closed form, but he can compute it numerically from this equation. He can decide on the optimal value of reward parameter R star. Okay. In this case, again, we have a Stackenberg game, but it's a bit different than the one we were discussing before, because now the aggregator announces his incentive parameter R, and then each of the users compute the equilibrium, and then they toss a coin, each of them, and they decide whether to participate or not. So we may have instances where the users really form the target total flexibility, and instances in which the users do not make it to offer the total flexibility with the same aggregate incentive parameter R. So in this graph, we have numerically investigated with my colleague, Professor Papaioannou, how the participation probability depends on the number n of users, on the flexibility offered by each user, and of course, on the unit reward parameter. The utility function we have assumed is that just very simple, that the utility, when they consume X amount of energy, is just square root over X, which y has to be concave. And this is a very simple formula with this shape. So actually what we see is that the equilibrium probability does not necessarily have to be close to 1. Because if we have, let's say, 10 users, but 15 users, like in this case, but I only need 10 of them to participate in order to make the total flexibility, then we see that with the approximate participation probability of 0.5, this is the optimal equilibrium probability for actually the Nash equilibrium probability for the users. So what does the aggregator make? Well, it depends. If the aggregator gives a high percentage of his reward, then he will make very low profits. You see here that the per unit reward that the aggregator earns from the flexibility market is 35. And so we see here that with rewards close to 25, we have very little profit by the aggregator. And if we go, and if we have even lower incentives, lower reward from the flexibility market, then we can see that the total profit of the aggregator may drop as low as 0. So it's interesting that the optimal rewards of the aggregator are, let's say, not on the other side of the curve. So what happens is that we have seen this quantity and the necessary condition that, namely, that this quantity is lower than 1. So one may think that the lowest possible rewards come from this necessary condition. What actually happens is that there is a gap. So if we just offer the lowest rewards, then again, they are so low that the users are not incited at all to participate due to the cost possibly incurred. And in this case, the problem is still not feasible. So we see that from for every curve, a lowest point where we have the equilibrium probability can be solved, and actually the equilibrium with mixed strategies is feasible. Okay, so and we see that either the curve is decreasing, which means that the aggregator should just offer the lowest rewards that make the problem feasible. What does it mean feasible? It means that the Nash equilibrium is indeed can indeed be defined, or just a little bit, if we have a big margin, we can increase, let's say, a bit the rewards in order to attain slightly better participation probability, and then it drops abruptly. So, as I said, this is work in progress. And so we have so far assumed complete information again, because we have this quantity delta U, which we have assumed that it is known by aggregator in order to solve the equation with the equilibrium participation probability, and then decide on R star on the basis of this of the numerical outcomes of this equation. So we're currently investigating the case of incomplete information, but as I said before, it's a little bit different than the case where I just expect a deterministic response, best response by the user. Okay, because we will have an iterative solution, which is based on the best response by the user, in order for the aggregator to discover the off-band incentives parameter. And of course, we have started thinking of relaxing the assumption of completely symmetric users. Like, for example, consider two cases: small apartments in a dormitory and big apartments in a dormitory. So not just or consider that we have, let's say, not identical users, but users whose utility function has some parameter which comes from the same distribution. So identically distributed users. So I think we have almost, I took 10 more minutes. Thank you very much for your attention. Again, it has been a pleasure and great honor for me to be here with you and give this seminar. And you can find more information on the website of our group and also in the website of our project. Thank you very much again. Mille merci. Have any questions, please? Okay.
It's on the game theoretic question. So, I mean, how you alluded to this Nash equilibria, and so the number of players is this capital N, right? So, which is large, right? So, how difficult is it to compute this Nash equilibria, and can one use also perhaps mean field approximations or things of this type?
All right. Initially, we had thought that it was more difficult in the symmetric case because we had, let's say, the difference of two upper tails. But then we were simplified in this formula, so it became a bit easier. In the general case, it's, of course, if you have, let's say, each user being characterized by his own probability, then we have a system of n equations, and this would be very computationally intensive. That's why we said that even if we depart from the simplest symmetric case, we will have, let's say, either two loops, or a parameter, and in which case we may have some, let's say, expected value approximation, etc. So there was another question also?
Yes. And there wasn't a question that I completely understand the sense, but it seems to contradict some intuition. So I guess if big N is big,
Yes.
as a single user, my action is less determinant. So
Yes.
this would decrease my probability to participate. But it seems that the formula says the opposite. Because I mean, if my action doesn't change anything, I will not participate. I will make free riding. And
But it also depends on how many users you need.
Yes,
to make
exactly.
it. So there are two factors.
yes, fixing this N mean, how does N work? Because it seems the intuition would say the more the N, the less the probability.
Yeah.
But the formula was saying the opposite. I think, or I may
Yeah, but-
miss it. The 27, page 27.
See?
Twenty-seven.
Okay, that's good.
Because it's X. It seems that this probability increases with n. So it's a counterintuitive. Maybe if you have an explanation of this.
Okay, but I think it will depend on the ratio between n and n mil.
Okay.
Okay, because you have also n capital N
Yes.
in the other side as well. So
Mm,
that's
mm.
why I looked at these figures and these graphs here. And let me just see if I can find an easy example. So to compare. Mhm. Just give me a minute, please.
Yeah. No.
I was looking for a case where we have different n but the same n,
Yeah.
but they don't match.
Yeah, I tried to
Yes,
catch
yes.
and there are not.
But the last point, we will make sure in the paper that we have, we will rescale the
Right.
problem to see how the parameters are affected in this case. So
Mm.
to have different pairs of parameters, but with this, but just with the same proportions.
Yeah.
This is what we
It
do.
can be an interesting counterintuitive
Yes.
effect.
Thank you.
So I have other two questions. Maybe it's late. No?
We
Yes,
can
maybe
take
yes.
them
Offline we can
Yes.
take.
We're very glad. Again, many thanks.
Thank you.